back here, and I'm going to introduce some of the faculty and a student who's involved in the Advanced Materials Center Solar Concentrator project. This is Brad Johnson, who's the chair of the physics department, John Gilbertson, who's the chemistry professor, and Chris Westcott, who's a master's student at Western. They're going to tell you a little bit about some of the prototype work they're doing for their solar concentrator project.
So what we're trying to accomplish is called luminescent solar concentrator. The basic idea is that we use fluorescent dyes, organic fluorescent dyes, to capture the sun's energy and then trap it within a cheap piece of plastic, kind of like what you see here with this commercial piece of plastic. Ultimately what this allows us to do is use a lot less surface area of traditional photovoltaics, which are the most expensive part of any solar energy generation method. In addition, it's a very resilient technology. We've purposely punched up this piece of plastic here to show the resilience of it. You can punch holes in it, scratch it, and it'll still function just fine. Efficiency might go down a bit, obviously, but it'll still work. Try and do that with a regular photovoltaic system. You break a single one and an entire array goes down. But the basic idea is we use a series of fluorescent dyes to capture all of the sun's visible wavelengths of light. That gets converted down to very red light, which is very efficiently turned into energy by photovoltaics. And we actually have a small little prototype here that accomplishes that. That just allows, all we have here is a piece of plastic, kind of like what you see there. Around the edges are very small strips of photovoltaics around the edge, and then the light hits the surface of the plastic, gets captured by those fluorophores, gets trapped within the plastic, travels all the way to the edge, and then gets converted into electricity through the traditional means. And as I said, the overall goal of this is just to reduce the price of generating solar electricity, ultimately by a factor of, I believe, what did we go for? About 1/10? And so about 1/10 of the current cost.
That would bring it in line with the competitive with, say, hydroelectric. So it's still a little more expensive than, say, coal or natural gas. So getting there. Yeah, that factor 10 would be a big thing. But plus, aspects like this durability thing make it so it'd be an excellent sort of technology for portable power generation. There are lots of applications where you just need to set up something where you can generate power portably. It's durable. You can put up with a lot of stuff. And it's also good for the Northwest. And you can see what you see coming out. It's capturing all of the diffuse light coming to it from every direction. That's one of the things that makes it good for the Northwest, is that you don't really need direct sunlight for it to work. You see the edges. On the edges is where the actual is. Yeah. So one area, and you got less sunlight. That's right. So the basic idea is just like saying, if I had a big lens, right, I could take the solar intensity spread over an area like this, and I could concentrate on it to a very photovoltaic, that would be the same number of photons, the same amount of light that I could make electricity out of as if I had made a piece of photovoltaic. Well, it's not quite that simple, and in fact we're working on very structural designs to make it to optimize just that question. There are lots of questions that go into that. This business, the ratio of that to this is something that depends on a lot of stuff. So yeah, that's one of the optimization problems we're actually working on. So are there a number of layers on panel, or
there can be. There's actually several different methods. Different photovoltaics convert light more efficiently at different wavelengths of light. So you could ideally have, imagine 4 sheets of plastic, one with blue, yellow, orange, red, all those, each with their own little photovoltaic on the edge that has a better chance of converting that photon into energy. And so you can imagine having multiple layers, but you can also have all of them in one layer. And the idea behind that is that the emission of one fluorophore will be absorbed by the next in the line. And what this happens is the blue light eventually gets transferred all the way down into the red. And so you can use just a single type of photovoltaic, just silicon, imagine, that could convert very highly, or with a very high efficiency, all of that light. Because you've turned that blue light, which normally isn't converted very well, to the better wavelength.
So we can design molecules that will step that out.
The project has sort of several aspects to it. One, where John's expertise expertise comes in is it's in building the dyes themselves. Sort of the molecular chemistry that goes into building the dyes. And then there's part about optimizing the structure and capturing the photons of the light. And yeah, there's some more ideas associated with that, and linking them all together is kind of why we built this team. Just to kind of give you just a little piece of overview, this project is funded by the National Science Foundation under a project called Solar. And one of the ideas that they put out was we need to have people coming from different disciplines to solve these problems. So they forced the proposal to contain. So the team contains myself and another physicist, chemist, John, and another chemist, and then there's a mathematician on the team as well. And all of us are working together on the different aspects of putting this whole project together. That's kind of one of the unique pieces of this thing. And all of this falls under the auspices of the Advanced Material Science and Engineering Center at Western. That's one of the reasons that center was developed.
That concept patentable?
It is patentable. We have 2 patent applications right now.
So we're going to have to move on. I can see the other business starting to back up a little bit. So we're going to have to move over around the corner.
Sorry about that.
Thanks, guys.